Asynchronous many-tasking runtimes, like HPX-5, tolerate latency through asynchrony and the overlap of communication and computation. Adaptive runtimes can dynamically map communication and computation to available resources for load balancing. The HPX-5 runtime is based on the parallax execution model and provides lightweight threading, active messaging, and synchronization, all within the context of an active global address space. It currently balances local work using a work stealing scheduler and has the ability to transparently move data within the address space to balance global execution. The HPX-5 interface and runtime library virtualizes the system resources such that HPX-5 applications are no longer tied directly to the number of cores or the network topology of the underlying allocation. This capability allows programmers to over-decompose their applications and rely on the runtime to efficiently and dynamically map domains to resources. This visualization demonstrates the effect of over-decomposition on the LULESH proxy application developed at Lawrence Livermore National Labs. This regular, mesh-based hydrodynamic code decomposes the problem space into a cubic number of domains. Each time step is characterized by 3 neighborhood communications, where each domain communicates with some subset of its face, edge, and corner neighbors, and an all-reduce. The visualized executions here are based on a raw translation of the MPI version to equivalent HPX-5 code, restructured to use a non-blocking all-reduce operation. For simplicity, these visualizations recorded for a problem size of about 7 million points distributed across 8 ranks, totaling 64 cores. However, the implementation is commonly run on more than 20,000 cores and billions of points. The visualization loosely couples the application-specific domain execution with that of the runtime behavior. Application domains are depicted as gray boxes laid out according to their logical positions. Messages and communication events are shown as dynamic yellow annotations. The hierarchical, non-blocking all-reduce is rendered through a ring projection surrounding the domain grid. The all-reduce is implemented using a rooted reduce broadcast algorithm with optimized local reductions and a fat network tree. The visualization represents this implementation using reduce and broadcast nodes for each rank and a node for the network root. The simulation visualized on the left decomposes the problem into 64 domains with about 100,000 points each. This domain size is based on the traditional MPI decomposition of the same problem and sends relatively large neighborhood messages and performs extended computation. Messaging and computation phases are clearly visible here. The simulation visualized on the right over-decomposes the same problem into 512 domains with about 10,000 points each. This decomposition is not possible with the original MPI code, as it does not effectively execute on 64 cores using traditional MPI runtimes. This visualization demonstrates the fine-grained structure of the over-decomposed algorithm, the dynamic and asynchronous nature of the HPX-5 runtime, and the resulting continuous communication computation overlap. The over-decomposed execution outperforms the coarser decomposition by approximately 20%, and the MPI reference implementation by about 10% at this scale. This is a result of 2 key effects. The first is model-based. HPX-5 can schedule domains for execution as soon as their outstanding dependencies are satisfied, and thus the smaller domains can begin processing sooner. The second is problem-based. The smaller domains fit in the L1 cache, and thus the execution of each domain is accelerated in the over-decomposed case. In essence, the HPX-5 execution results in a dynamic cache blocking of the algorithm when the domain size is chosen appropriately. The current version of HPX-5 can be downloaded from Indiana University's Center for Research in Extreme Scale Technology at hpx.crest.iu.edu. Thank you.